Hi and welcome to Chemipedia. So in this video I am going to discuss about zero order reaction. We are going to discuss about what is meant by zero order reaction as well as rate constant equation derivation for zero order reaction. Okay, first let us see what is zero order reaction. This is the definition of zero order reaction. Chemical reaction whose rate is independent. Chemical reaction whose rate is independent of concentration of any of the reactant. Okay, so you have a chemical reaction. The rate of the chemical reaction is measured, whereas rate of that chemical reaction does not change with respect to change of concentration of any reactant. Then that reaction you can call it as a zero order reaction. Chemical reaction whose rate is not depending concentration of any of the reactants. Okay, so right. So now let us see some example for zero order reaction. Photochemical reaction between hydrogen gas and chlorine gas is an example for a zero order reaction. Reaction between hydrogen gas and chlorine gas. That is H2 gas reacts with Cl2 gas in presence of sunlight. H nu is symbol for sunlight, giving 2 moles of hydrogen chloride gas. Okay, so this is an example for zero order reaction, which means rate of this reaction is independent. Rate of this reaction, I can write rate law for this reaction as rate equal to rate constant K into concentration of H2 power 0, then concentration of Cl2 power 0. So power 0, which means rate is not depending concentration of both the substances H2 as well as Cl2. So it is a zero order reaction. So hydrogen chloride formation reaction rate never depend concentration of H2 and Cl2. Whatever concentration of H2 Cl2 you use, it takes a fixed time for completion. Okay, right. Then the second example, decomposition of nitrous oxide in presence of platinum, or decomposition of nitrous oxide on the surface of platinum metal. Okay, right. So this is the equation N2O gas on dissociation giving N2 gas, nitrogen gas and oxygen gas. Okay, so this is also another example for zero order, in the sense rate will not depend concentration of nitrogen nitrogen oxide, or that is nitrous oxide actually. Okay, right. Then another example, third example, iodination of acetone in acidic medium. Iodination of acetone in acidic medium. So this is nothing but acetone. Acetone is a ketone, isn't it? With formula CH3CO, CH3. Acetone, which we also call it as propanone, isn't it? A ketone with 3 carbon atom, propanone. With this, when we add iodine in presence of acid catalyst in acidic medium. Okay. Now what is happening is, one of the alpha hydrogen is getting substituted by iodine, so that you get a product CH2I CO CH3, what you call it as monoiodoacetone, monoiodoacetone plus byproduct on the HI. Okay, so this is a zero order reaction with respect to iodine. Okay, so here also the rate of this reaction is not depending concentration of the substances, so this is another example for zero order reaction. Okay, right. So now let us see how to derive integrated rate equation for a zero order reaction. Okay, so now this is a general chemical reaction. Reactant A is giving product. Now I am going to write rate law and rate expression for the above reaction. Rate law is rate equal to rate constant. Rate law, rate equal to rate constant K into concentration of reactant, that is concentration of A power 0. So here we write A power 0, which means this is a zero order reaction, in the sense rate does not depend concentration of substance A, isn't it? So that we write it as A power 0. So in the concentration term, if you use power 0, which means rate of that particular reaction is not depending concentration of that substance. Okay, so rate not depending concentration of A, so I write it as A power 0. Right. A power 0 is nothing but 1, isn't it? Right. Then for the same reaction, rate expression, rate is equal to change in concentration of reactant A divided by change in time, that is minus dA by dt. Okay, the rate law equation I take it as equation number 1 and the rate expression 2. Okay, right. Now in both equations left side you have rate, isn't it? But now you can equate on right hand side. Therefore from equations 1 and 2, so we get minus dA by dt. Second equation right side, minus dA by dt equal to first equation right side, K into concentration of A power 0. Okay, so as I said already, A power 0 is nothing but 1, isn't it? So that right hand side you can have only the term K. Now just I am going to bring this dt on right hand side. So the finally it becomes minus dA equal to K dt. Okay. So equation number 3. Now this equation 3 has to be integrated on both sides using limits. Okay, right. So now we get this one, isn't it? So there is a minus sign before d of a, isn't it? So I retain that one. Then minus integration of dA with limits a naught initial concentration of reactant, a concentration of reactant at time t is equal to K constant. So I bring it outside. So K integration of dt with limit 0 time and t time. Okay. So integration of dA is nothing but a. Integration of dA is nothing but a. So I retain the minus sign, lower and upper limits. Then K constant. Then integration of dt is nothing but t with limits 0 and t. Okay, right. So now in the next step I am going to substitute the limits. Okay, so that first I substitute upper limit. So minus sign common, a minus a naught, isn't it? Okay, which is equal to right side K into, in the place of t, upper limit t and lower limit 0, but t minus 0. Okay, so finally the equation becomes, this minus sign is common for both, isn't it? So that the second term will become positive. So I write the second term first, a naught concentration minus a concentration equal to Kt, isn't it? Keep K alone left side, so that K is equal to a naught concentration minus a concentration divided by T. Okay, so this is nothing but rate constant equation for a zero order reaction. Okay, right. So now what is the unit of this? What is the unit of K for this reaction? Okay, right. Now in the K formula, in the numerator we have concentration. This is nothing but concentration terms, isn't it? In the denominator we have time, isn't it? But therefore the unit of numerator is nothing but mole per liter. The denominator time, so unit is second. When you bring the second to the numerator, so what you get is mole per liter per second. Okay, so that is nothing but the unit of rate constant K of a zero order reaction. Okay, so K unit is mole per liter per second, and we know very well that this is nothing but the unit of rate also. Rate unit is mole per liter per second, isn't it? Mole per liter per second, because rate is nothing but change in concentration divided by change in time. So mole per liter, change in concentration, change in time, second, when it comes up per second, isn't it? So that rate unit and zero order rate constant unit are nothing but same. Okay, right. And after this we are going to derive that half-life period formula for a zero order reaction. Okay, so already we have discussed what is half-life period. So time required to reduce 1/2 of the initial concentration of the reactant. Okay, in the previous video I have discussed that half-life period of a first order reaction is independent of initial concentration, isn't it? A naught, it is T of is independent of A naught, isn't it? But here in zero order reaction, half-life period of zero order reaction depends A naught. Okay, that we are going to see in the derivation. Okay, right. Now first I have written the rate equation for the zero order reaction, that is K equal to A naught minus A divided by T, isn't it? So what is derived in the previous case? Now when time is T of, when time is half-life time, then the concentration of reactant at T of is equal to half of the initial concentration. Okay, but when time is T of, the concentration of A will be equal to A naught divided by 2. Okay, so I am going to substitute both this in the above equation, so that I am getting K equal to A naught minus, in the place of A I have substituted A naught by 2 whole divided by, in the place of T in the original equation I have substituted T of, isn't it? Okay. Now so in the numerator I take LCM, the first term will be multiplied by 2, isn't it? 2 into A naught minus A naught divided by this 2, you can bring it down. So 2K, I just rearrange this also. I bring T of on left side, K to the denominator. So finally you get this one. Okay, T of is equal to 2A naught minus A naught divided by K. 2A naught minus A naught is nothing but A naught, isn't it? So the final T of formula, T of is equal to A naught concentration divided by 2K. Okay, right. So this is a half-life period formula for a zero order reaction. Okay, right. Now look at this formula. Here you have the initial concentration term. A naught is nothing but what? Initial concentration, isn't it? So it is in the numerator, which means this T of and A naught are directly proportional with each other. Okay, so that is half-life period of a zero order reaction is directly proportional to the initial concentration of reactant. Greater the initial concentration of reactant, greater will be the half-life period, and vice versa. Okay, right. So this is a point you have to remember. In case of zero order reaction, half-life period is directly proportional to initial concentration of the reactant, that is T of is directly proportional to A naught, whereas in a first order reaction T of is independent of A naught. Half-life period of first order reaction does not depend on initial concentration of reactant. Okay, right. Thank you. So keep watching other videos also. Thank you very much.